Okay, so this is going to be 4.1. The 4.1, we go with the preliminary. Okay, so this is it. Second order differential equation. Second order linear differential equation. Linear differential equation. So this is going to be our target. The definition pairs. What are going to be considered equation to be linear? Okay, a differential equation. Differential. Okay, the differential equation of this form, of the form. So the standard form is going to be the following. You get the y double prime for the second order, okay? Then it's going to be plus p of x times y prime. Already a standard notation that we're going to use. Then plus q of x times y, okay, equal to the r of x. This is going to be the case. Okay, these p of x, q of x, r of x are nice continuous function, okay, where p of x, q of x, and r of x. Okay, they are nice, are continuous function. Continuous functions. Okay, so the differential equation of this form, this information is going to be called, okay, this equation is called a second order. Okay, that's it, that's the name, a second order linear differential equation. Linear differential equation. That's it. Okay, so this is a situation we're going to have. You see the coefficient of the y double prime we consider to be 1, because there are a couple of formulas that we're going to create it to solve these problems. Those formulas depend on this coefficient. So if this coefficient is anything other than 1, equation is not a standard. You have to divide it by that coefficient to take care of it. Otherwise, your formulas, your solution would be very complicated. Okay, so make sure you do this one all the time. Okay, so I'm going to refer to this equation. In order to solve it, sometimes we are going to make this one easier, if you like. This is number 1. R of x is going to be a function of x. If this R of x happens to be equal to the 0, result of the equation is called homogeneous second order differential equation. Okay, so if R of x is equal to the 0, then we're going to have a second one. Second one would be y double prime. That's px times y prime. That's qx. Okay, qx times y equal to the 0. I refer to this one as equation number 2 for the time being. Okay, this is going to be called, it's called the homogeneous. Okay, it's different from homogeneous that we did before. It's called homogeneous, okay, homogeneous linear equation. Homogeneous, okay, again, second order linear differential.
Can you
Differential. Okay, homogeneous linear differential equation. Okay, it's going to be homogeneous linear differential equation. It's going to be a homogeneous differential equation, okay, corresponds or to the or associated to the number one. Okay, so this is going to be the case. Okay, any question? Let's have some examples to get to know them. So look at these equation, various format, various notation that we may be given. The first one is y double prime plus x squared y prime, okay, minus 3xy equal to the e to the x. You see, that's it, it's a linear. You see, you should have only y double prime, and y. If you have y squared, it's not linear. If you have y prime, it's not linear. We already talked about the definition. Okay, and this is non-homogeneous because r of x is not z. Okay, that's the case one. In this case, for example, p of x is x squared. We should be able to identify it. Q of x would be negative 3y, and r of x is e to the x. The second one, y double prime plus 5y prime, okay, minus 4y. This is going to be the case. Minus 4y equal to the 2 sine x. What is special about this one if you compare it with the first one?
No x's on the left side.
No x's on the left side. Yeah, this means the coefficient, okay, the coefficient of the y double prime, y or y prime, they are all constant. And that would be very important for us, okay? And we're going to investigate the solution of this group first, okay? So we call it a linear equation with the constant coefficients. A linear equation with the constant coefficient, because all the coefficients are going to be constant, okay? That's number 2. Let's see, number 3. Number 3 is this one. Okay, y double prime. Okay, y double prime minus y equal to the x squared plus 1. It's another one. In this case, you don't have the y prime. It's okay. Again, it's a okay. This is a linear equation. Okay, number 4. Number 4 is y double prime plus 4y prime minus y equal to the 0. What's special about this one?
Genius.
It's homogeneous. R of x is equal to the 0, so this is homogeneous equation. The other one were all non-homogeneous, okay? And the one to remember is the last one, number 5. Number 5 is x, y double prime. Okay, so this is going to be number 5. Number 5 is x, y double prime plus 5x cubed y prime minus 9y equal to the 0. Okay, what's different about this one?
Y prime has a term.
Y
Y double prime has
double prime, yeah.
has a
The
term.
coefficient of the, you see the coefficient of the y double prime is not 1. So it's not in the standard form. So quickly divide it to get it standard, okay? Divide by all the formulas that we're going to have, coefficient of the y double prime is 1. So divide by x, we assume that x is not 0, so that we can divide it. So that give you y double prime plus 5x squared y prime minus 9y equal to the 0. So this is a kind of standard one that you know that we can have. Of course, it's going to be 9 over x. Okay, y double prime plus 5 x squared y prime plus 9 over y equal to the 0. Okay, we assume that x is equal to the 0. Okay, so this is our definition. Okay, any question? Now, how are we going to solve this equation? That's what is going to be the nature of the solution of this equation. So what we're going to do, we are going to investigate a little bit about this type of the equation first. Okay, then we go for it. There are a couple of things that we are going to investigate. The first one is going to be, you see, we have two equations, number one and number two. If you want to find the general solution of this equation, okay, general solution of this equation, that's going to be your purpose. Okay, the purpose is this equation number one would be given to, and then you would like to find the general solution. So what we can do is we can make it homogeneous first. That's homogeneous. When we get a homogeneous, we try to solve this one. Usually this is easy to solve, and we have 3-4 methods to solve it, and we're going to discuss it. So we solve the homogeneous one, okay, the corresponding homogeneous equation, and we find the general solution. This general solution we refer to as a YC. Okay, Y for the solution, C for the complementary equation, or okay, the equation associated with R of X. We call it YC. So we find the general solution of a second one, we call it YC. Then we go back and we try to find one particular solution of the first one. So YC would be the general solution of the homogeneous one. YP would be the solution of the non-homogeneous one. Now we can prove that if you put them together, this combination is going to be, again, a solution for number one. This combination, YC plus YP, we are going to refer to it as a general solution of a, okay, second order linear differential equation. So I'm going to prove it for you. It's not bad to see how we prove this. Okay, we prove it, and later on we are going to use it. Then we know the road plan. So we get the nature of the solution, then you have to go find it. So you have two jobs. The first job is how we're going to find those YC, the general solution of the homogeneous equation, and then how we're going to find the YP. We have various methods to be able to, okay, to do this. So that would be what we are going to do for the rest of the couple of sections that we're going to have, okay? So just the nature of this, okay, to know it is not bad, okay, to get proof. Remember it? So what we're going to investigate is what is the general solution? Okay, general. This is it, general solution. What is the general solution of the, okay, of the second order linear differential equation, okay? Linear differential equation. Differential equation. Want to investigate this. Okay, the claim that I just made, I'm going to prove it. This is what we are going to do. You see, if Y sub C, YC is the general solution, will be general solution of the homogeneous equation, homogeneous equation. This is the equation. Y double prime plus PX Y prime plus QX Y equal to the zero. Remember equation number one. The equation number two. It doesn't matter. In this case, we call it number one. If YC is the general solution of the homogeneous equation, okay, and YP is, okay, is a particular solution. It's a particular solution, okay, of the non-homogeneous, non-homogeneous equation. Now what's going to be non-homogeneous one? Y double prime. That's PX Y prime. That's QX Y. Okay, equal to the R of X. Number two. If this is going to be the case, okay, then one can prove, and we are going to prove it. One can prove that y equal to yc plus yp. Y equal to the yc plus yp is also a solution. Okay, it's also going to be a solution of that differential equation number one. Okay, of the differential equation. That's a 2. Okay, then one can prove that y equal to the yc is also a solution of the equation. I just repeat it. This is it. Y double prime. That's px y prime. That's qx y equal to the rx. Okay, in this case, y equal to yc plus yp is going to be called, it's called the general solution. General solution of that homogeneous of the equation, of the differential equation, of the differential equation. Okay, this one that we did over here on the origin. Okay, let's prove it. I'm going to prove this one, but you should prove. You want to prove that yc plus yp is the solution of this equation. If you want to find to prove a different given function is the solution of a differential equation, so what are we going to do? You have to plug in into the equation and show that that expression, that function would satisfy that equation. If you prove that this yc plus yp, it's satisfying the equation, the star equation, in that case, it's going to be the solution of your equation. So I'm going to prove it for you. So what you know, you see, note that. What do you know about the yp and the yc? The first thing, you know what? You know that yp, remember, yp is a solution of what? Of this equation, of the equation non-homogeneous one, of the equation number 2. So it should satisfy the equation. Drop it into equation number 2. So you are going to have y double prime p. That's p of x times y prime of p. Let's say q of x times y of p is equal to the r of x. This is because yp is the solution of this equation. Okay, any question? So what do you know about yc? Yc is the equation of that equation, okay, number 1. Yc, okay, so yc is the solution. Is the solution of the equation of a non-homogeneous, of a homogeneous one. Equation number 1. So it must satisfy that equation. So y double prime of c plus px times y prime of c plus qx times y of c must be or is equal to the 0. Is equal to the 0. Okay. So remember what you want to prove. You want to prove that the yc plus yp is the solution of this equation. So substitute in the left side over here. See what's going to be the result. Okay. So this is going to be the case. Therefore, so what I'm going to do, I'm going to look at this equation, and I'm going to check yc and yp in that equation. So substitute. If you substitute for y, substitute yc plus yp. So that gives you yc plus yp double prime plus px times yc plus yp prime plus q of x times y times yc plus yp. I want to prove that this is equal to the R of x. If you show that this is equal to the R of x, this means yc plus yp is the general solution of your equation, and you're done. So do the algebra. So what can you do is just apply the definition. You know, this is second derivative. Second derivative is linear, so that give you what? So this is going to be equal to, this would be yc double prime plus yp double prime. Over here, this would be plus p of x. You differentiate the parentheses, you drop it in, okay? Yc prime, yp prime, derivative of the sum of two functions is the sum of the derivative. And this is going to be plus q of x times yc plus yp. Remember, I want to prove this is going to be equal to the R of x. Okay? So multiply these parentheses over here, simplify it. So it's going to be yc double prime. Okay? It's going to be yc double prime. I'm going to distribute this in. Plus yp double prime plus this would be p of x times yc prime of c plus p of x yp prime. Okay, now multiply the qx inside plus q of x times yc plus q of x times yp. Okay, I just distributed it. So what I'm going to do, I'm going to group them together so that I'll be able to use these two identities that I put over here. So to group them together, I'm going to group this. Look at this one. One with the yc, 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 yc. So group these together. What are we going to have? If you group them together, that give me y double prime of c plus px yc prime plus qx, okay, yc. This is going to be first group. Then the leftovers. What's going to be the leftover? So from the leftover is going to be plus new group. One with a p, yp prime plus px times, that was double prime, is a prime, plus qx, okay, qx of yp. This is how we group them together. Okay, now from equation number 1 and 2, what do you have for these two groups? What is the first one?
R of x.
It's R of x. But remember, yc was the solution of the non-homogeneous case. So this part over here, this part would be R of x. R of x because of the equation, you see this equation that you know, sorry, it's not R of x. Yc would be 0, okay? This would be 0 because it's a homogeneous on 0. And what is this one? What the yp would be R of x. Because the yp was a particular solution of the non-homogeneous, yc was a solution of homogeneous. So this would be 0 plus, this would be R of x. So altogether would be R of x. So this means yc plus yp is satisfying this equation started we talk about it. So this basically means yc plus yp is the solution of a non-homogeneous differential equation. Okay, so the conclusion is that y equal to the yc plus yp, you can call it the general solution of the, okay, is going to be the general solution, the general solution of that equation that I call it a star, or a general solution of a non-homogeneous second order differential equation. So that gives you the roadmap. in order to find the solution of these equations. Okay, we proved it. So what your job is go and find the YC and the YP. Okay, so what we are going to do, we cannot rush to find them. Okay, we have more to do. So we are going to divide this one into different parts. The first part, we are looking for the YC, and the second part, we're going to look for the YP. I give you a break now. You come back, we have to work on the YC to see if we can do what. We work on this one first, and then we come back and talk about the YP. Now, the problem is going to be this one, solutions of the. So we focus on the solution. Okay, solutions of homogeneous linear differential equation. Okay, linear differential equation. Okay, this is going to be the equation that I'm going to focus on. So we get the y double prime, px y prime plus qx y double prime equal to this. We're going to investigate this, okay? Then we go back and investigate y. Now let's see what's going to be the situation that we're going to have for this. Now, in order to find the homogeneous, in order to get the general solution of this type of equations, okay? So what we can do is we can try to find two particular solutions, y1 and y2. If you find two solutions like y1 and y2, then we can prove that a linear combination of y1 and y2 is also a solution. What's a linear combination? Linear combination is like, 2y1 plus 3y2. Okay, C1y1 plus C2y2. If you are familiar with the notion of the linear algebra, what really we wanted to prove that when this type of equation would be given to you, there are infinite, yes.
Wait, why does the Q of X have a Y double prime?
Answer, that must be why. Why, thank you. Okay, so what we can do really is this equation would have infinitely many solutions. So if you are familiar with the notion of the linear algebra, we can collect all the solutions of this equation together, and we can define two different operation of the addition and the scalar multiplication. This means if y1 and y2 are going to be solution of this equation, then y1 plus y2 is also a solution. And if y1 is a solution, 5 times y1, k times y1 is also a solution. If you have a system of objects that satisfy this type of condition, or you can define these two types of operation, then this system is going to be called vector space in linear algebra. If you have a vector space in linear algebra, there are some special vectors that can generate the full space for you. Like in R3, remember in R2, in R3, you have the vector ijk. Remember, every vector in three-dimensional can be written as a linear combination of ijk. In that case, ijk is going to be called a standard basis. A standard basis for the three-dimensional space. In the vector spaces, you can create something similar. If you create something similar, then everything else would be the linear combination of this. So the way we are going to get the solution of this type of equation is this one. We are going to find, this is the equation, differential equation of a second order. Since the second order, the basis that we're going to be looked for would have only two members. So for the two members, we find two solutions of this one, y1 and y2. Since you don't have the tools of the linear algebra, or we don't want to bring it, we are going to prove somehow how those two solutions are going to be a basis. If we can prove that they're going to be a basis, then it's clear. C1y1 plus C2y2 is going to be the general solution of a differential equation. This is the equation of a second order. If it's going to be third order, you need three vectors. Y1, Y2, Y3. If you have a differential equation of the n order, you need n vectors. So that's the idea. Since we don't want to get involved with the linear algebra a little bit, so we are going to do it in a classic form. In a classic form means we create whatever we need here, okay? But this is the fact. That is going to be, part of the more general version. That's why step by step, we are going through that procedure. That how we're going to define two solutions of this equation that make it a basis, okay? Then every other solution is going to be linear combination. We are done, okay? So I'm going to use those, prove those preliminary for you first, okay? It's nice to prove it, okay? To get a better understanding. At the end, everything will be nice. In 2 seconds, you can find the solution of this equation. And you have to, build up the formula. Okay, so this is going to be the case. Now, what we are going to prove is this one. Okay, if going to investigate the nature of the proof solutions, and then we come back. Get two solutions. If y1 is a function, okay, y1 and y2 are any two solutions of the equation is going to be homogeneous of the equation, then we can prove, or one can prove, that any linear combination, okay, that C1 Y1 plus C2 Y2, okay, you can call it Y. So one can prove that Y equal to the C1 Y1 plus C2 Y2 for any constant, okay, any constant C1 and C2 is going to be also a solution, okay, a solution of the differential equation. That's step one that you have to prove. Okay, it's easy to prove. Okay, in 2 steps. How we're going to prove it? In order to prove, as we did it before, you have to prove that this combination is satisfying this equation. So they wrap it into the equation to see if this is satisfying. Okay, so they wrap it into this equation. So you are going to have a C1 Y1 plus C2 Y2. Okay, as we did it for the other one, double prime plus PX times C1 Y1 plus C2 Y2 prime plus QX times C1 Y1 plus C2 Y2. I want to prove that this is equal to the 0. If I prove this is equal to the 0, so this means this combination is the solution of your equation, okay? So work on it. It's a derivative, the second derivative or the first derivative of a linear combination could be the same thing. So this is going to be C1 Y1 double prime plus C2 Y2 double prime. Okay, the next one, plus P of X times C1 Y1 prime plus C2 Y2 prime plus, we just distribute this one. You can distribute it now or just later. It's going to be Q of X times C1 Y1 plus C2 Y2. Multiply them together, group them together. We want to prove it's equal to the 0. Okay, so this is it. It's going to be equal to C1 Y1 double prime, C2 Y2 double prime. Distribute these. So it's going to be plus C1 P of X Y1 prime plus C2 P of X Y2 prime plus C1 Q of X Y1 plus C2 Q of X Y2. Okay, I just multiply them together. Now put the Y1s together and the Y2s together. Maybe I have to prove it's 0. Okay, look at the what we have. Look at the y1s. You have one here. Okay, this is it. And you should have one with the cube. And this is it. From this group, factor out the C1. If you factor out the C1, what's going to be the result? It's going to be C1 times Y1 double prime, okay, plus P of X Y1 prime, plus, what's the other one? Plus Q of X times Y1. That's the first group. Put the second group. What's going to be the second one? This green one. Now take the C2. It's going to be C2 times Y2 double prime plus P of X prime plus Q of X Y2. Okay, any question? Remember what was Y1 and Y2? Y1 and Y2, they were solution of this equation. See? Y1 and Y2 are solution of this equation. And you know that the function is a solution of the equation if that function satisfied in the equation. Satisfy means you can put the Y1, this result must be 0. And you can put the Y2, this result must be 0. Look at the first one. The first one is what? Y1 double prime. Px Y1 prime plus Qx Y1 is equal to the 0. So this would be 0. Because Y1 is the solution of the equation. Any question? Again, Y2 is the solution of this equation. Y2 must satisfy this equation. So this equation would be what? Y2 double prime, okay? Px Y2 prime plus Qx times Y2. So this is also equal to 0. That's it. So what you have is, this is it, C1 times 0 plus C2 times 0. The result would be 0. So we prove that function y equal to, you see, we prove that, therefore, y equal to the C1 Y1 plus C2 Y2. Okay, C2 Y2 is going to be what? Is also a solution. Okay, it's going to be also a solution of the differential solution of the differential equation. Okay, it's going to be solution of the differential equation eventually. Okay. So that gives you, yes.
So the reason why those both cancel out to 0 is because at the beginning we said that the original homogeneous differential equation is equal to 0.
No, the reason is we say that y1 and y2 are solution of the equation.
Yeah, but
Then we say is a solution like the one on the test.
okay.
We ask you to show that this is solution of the equation. This means it satisfies the equation. So that equation is given to you, equal to the 0 is given, and we are looking for the solution of this equation.
Okay.
Okay. Any question? Everybody understand what we are doing so far? So if y1 and y2, if you can find y and y2 somehow, then any combination. So as soon as you find the y1 and y2, you have infinitely many solutions. Infinitely many solutions. Now, the thing that we are going to do is, so if y1 and y2 is given to you, c1 y1 plus c2 y2 is going to be solution of the equation. We are looking for a general solution. If you're looking for the general solution, the next question is going to be if you have another solution. If y is just arbitrary solution, can you find y1 and y2? Okay, can you find this? Can you write that? You see, if y1 and the y2 is a fix that's given to you, so if I give you a new solution, if I give you y a new solution, can you write that y as a c1 y1 plus c2 y2? So in fact, we want to prove that other than these type of solutions, you are not going to have anything else. Okay, under what condition? Under what condition, if somebody give you another solution, you are going to guarantee that you can write the other solution as a C1Y1 plus C2Y2. Okay, so this would be a very crucial question that we're going to answer. Say conversely. Okay, that's going to be conversely. So the direct one was if somebody give you Y1 and Y2, Y equal to the C1Y1 plus C2Y2 is the solution. So conversely means if somebody give you Y, can you find a C1 and C2 so that Y would be C1Y1 plus C2Y2? This means you are not going to have any other type of the solution. So the conversely, this is going to be the case. If, okay, if Y is equal to the f of x, is any solution, is any other. Because we want to know you are not going to have any other solution. This is only one. So conversely, if y equal to the y of x is any other solution of the equation, okay, this is going to be the case. Can you find? Can one find? Can one find constants? Constant C1 and C2 so that this new solution is also of this form. Y is equal to the C1Y1 plus C2Y2. You see, you want to prove that this Y1 and Y2 that you created is very special. Okay, it's very special. I can give you all the possible solutions with this my Y1 and Y2. You only have to find, you see, you have to change the C1 and the C2 to be able to do it. Okay, let's say how we're going to solve it. Okay, so what's going to be the question now? The question is this one, you see. You have the Y1, you have the Y2, and you have the Y, 3 functions. The question is, can you find C1 and C2? They are constant. Can you find C1 and C2 that satisfy this equation? If you can find it, then we're done. We have a method to find it. Okay, now C1 and C2 are constant. There are 2 unknown. If you want to find 2 unknown, how many equations do you need?
3, 2, 2.
If you want to find 2 unknown C1 and C2, how many equations do you need? 2 equations. Okay, if you have a 2 equation, then you can create what? You can create a system of 2 equations and 2 variables and find it. So one of them is this one. Create another one. Can you guess? Remember, this is differential equation, of course.
Purple and green.
Which one? No, forget about the other. The only thing that you have is this. You see, you have y equal to the C1, Y1 plus C2, Y2.
So
Y is known, Y1 is known, Y2 is known. You want to find the C1 and C2. You need another equation to put them together. So it's differential equation. You haven't used derivative anymore. So what we're going to do is we differentiate this equation. The second one is going to be what? Y prime equal to C1 Y1 prime plus C2 Y5 prime. That gives a system of the equation. We solve it, we get a formula, then we test that formula. When you want to make sure that this Y1 and Y2 is the one. You see, remember from linear algebra point of view, if you have done that course, if a set of vectors would be given to you, there are 2 conditions for the set of vectors to be a basis. Anybody got the linear algebra course?
they have to span.
They have to span and
Oh, unique solutions, like they have to equal 0 or something. It's something like
what
that.
do you call it that?
Independent.
Of course, they must be independent.
Yes.
Independent vectors to be able to do it.
It's all that.
What we
purple
are going to
worksheet.
do really, we are cheating. We are going to do the same thing, but we do it in a classic way. Classic because this is differentiation, okay? And it's going to be the same thing if you have done that course, okay? And we arrive at something that we give you an exercise that, okay, let's differentiate it. If differentiate is going to be the result, y prime equal to the C1 y1 prime plus C2 y2 prime. That's it. I have a system of two equations, two variables. So let's solve it. Okay? There are different ways to solve this one. Okay, any suggestion? I'm going to solve this one. So I rewrite it here and I solve it because we need the formula that we're going to find. Okay, so there you are. I have a C1 y1 plus C2 y2 equal to the y. And I have C1 y1 prime, C2 y2 prime equal to the y prime. Any suggestion? Ordinary solution. If you want to solve a system of two equations, two variables, how can we solve it, Alan? What suggestion? Which method can we apply? There are two different methods. Remember, C1 and C2 are the unknown. Any suggestion? Yes.
Can we isolate one of the C's?
Yeah, we can do that, but there is another easier method.
My bad. Elimination?
Of course, elimination method.
Okay.
Yeah, eliminate it. That's it. That's it. Decide which one you want to eliminate. Remember, the unknown are C1 and C2. Okay, suppose you want to eliminate C2. Okay, so what I need to multiply, these coefficients. I multiply the first one by y2 prime, the second one by y2. I have to change the sign of one of them. Okay, I change this sign. So what's going to be the result? So the result would be, we get the first one would be C1, y1, y2 prime, plus C2, y2, y2 prime, equal to the y, y2 prime. The second one would be negative C1, y1 prime, y2 minus C2, y2, y2 prime equal to the negative y prime, y2. Okay, add them together. So these two would cancel out. This one over here. Okay, if you add them together, you can factor out the C1, or let me just do it, CY1, Y2 prime minus C1, Y1 prime, Y2, and the other one would be Y2 prime minus Y prime, Y2. Factor out the C1. So that gives you Y1, Y2 prime minus Y1 prime. Y2 is equal to the Y2 prime minus Y prime, Y2. Okay, so C1 would be, this is it. The top would be Y2 prime minus Y prime, Y2. The bottom one would be Y1, Y2 prime minus Y1 prime, Y2. Can I do this one all the time? Or I need a condition to be able to do it? Yes?
The denominator cannot equal 0.
Excellent. It can be done only if the denominator y1, y2 prime minus y1 prime, y2 is not equal to the 0. Remember, we are looking for a condition. This is C1. You can go and find the C2 as well, but we don't need it because we are looking for a condition that guarantees that this system would have a solution. So the conclusion is going to be, see this version over here. Okay, so the conclusion is going to be the system. Okay, the system would have a solution. It has a solution for C1 and C2. If only this is going to be Y1, y2 prime minus y1 prime, y2 is not going to be equal to the zero. In order to remember it, this is just a determinant of a matrix. Okay, in matrix form, you see in matrix form, it's going to be determinant of this matrix. y1, y2, y1 prime, y2 prime. You see the determinant of this matrix? Cross multiply, so that give you y minus y2 prime. Sorry, y1 times y2 prime, y1 prime, y2. Okay, this must be a non-zero number. So this would be a condition that if you have it, then that's it. If you have two solutions, y1 and y2, that satisfy that condition, y1 and y2 would be a basis for all the solution of your differential equation. So this means as soon as you find it with this condition, you say y equal to cy1 plus c2y2 is going to be the solution of your equation. This is a very important quantity. We refer to it as a Wronskian. So that was just my intention to arrive at the, otherwise I could have defined it right away. Okay, definition of a Wronskian, okay, I think it's a Polish mathematician. Okay, there you are. So the determinant. This determinant that we talked about. Okay, the determinant. We call it W, which is equal to the y1, y2. This is just for the equation of the second order. It can be done for the higher order too. Okay, which is going to be equal to the y1, y2 prime minus y1 prime, y2. Okay, it's going to be called. Okay, this is going to be called the Wronskian. The name Wronski. Okay, we call it the Wronskian. It's the name of a mathematician of the solution. Okay, Wronskian of the solutions y1 and y2. Okay, so our plan is completed now. So what's the conclusion? The conclusion is you want to solve this equation, find y1 and y2 first. We are going to give you a method to find it. As soon as you find it, show that the Wronskian of this solution is not zero. If the Wronskian is not solution, you got a basis for all the solutions. Quickly, you say y equal to the c1 y1 plus c2 y2 is the general solution of your equation, and you're done. Okay, so this is going to be the case. Therefore, this is going to be a situation that we are going to have. Therefore, the Wronskian of y1 comma y2 is not equal to the zero if and only if, in the language of the linear algebra, y1 and y2 are going to be linearly independent. If you know this type of expression, linearly independent in linear algebra. So this basically means, in this case means if you have the solution with a non-zero Wronskian, y equal to c1 y1 plus c2 y2 is going to be the general solution, general solution of a homogeneous differential equation. Homogeneous, can you see it? Homogeneous differential equation, the one that we started, y double prime, pxy prime plus qxy equal to the zero. So we created a nice road plan for the general solution of We know that if you find this is going to just your YC. Okay, we stay with this one, we are going to create some method to find it now. Now we have the plan, we know the situation is. So do you have some problems in your book for the time being, 4.1? Because this is almost 4.1. So I just give one example and then we are going to be ready. Then we have to decide how we're going to find those Y1 and Y2. There are different ways we're going to do it. We are going to consider the equation with the constant coefficient. That would be easy to find. There are other methods. One of them is that you need this Y1 and Y2. Sometimes you look at the equation quickly and you can find one of the solutions. If the solution is going to be easy, e to the x, x, sine x, cosine x. So we are going to create a method after this that if you have one of the solution, you'll be able to find the second one. Okay, this is going to be, so we are going to have several methods. Let's give one example. So we finish this one. So that is the nature of the situation. This is a equation of the second order. If you have a third order, the same thing. So we stop, we focus on the second. This is a 2x2 matrix. If you have the equation of the third order, you need the Y1, Y2, Y3. Then you have to have the 3x3 matrix. Okay, we are not going to go through those. Okay, so don't be surprised if you don't have any particular example or the problems, but you have some. So don't be surprised if you see this type of problems, and this is how we're going to do it. They give you the Y1 and the Y2, and they ask you to find the general solution. Okay, so you have to check the condition. Example. You have some problems in your book to ask to find the Wronskian, but we are not going to be concerned with those. This is it. This typical problem so far. Show that Y1 equal to the sine x and the Y2 equal to the cosine x are solutions. Okay, are solutions of this equation. Solutions of this equation, y double prime plus y equal to this. You know that you have to check the derivative inside to show that, and then determine the general solution. Okay, the general solution of the equation. Equation homogeneous, and you have two particular solutions. And you know that. If you can prove that the Wronskian of Y1 and Y2 is not zero, then you can give us the general solution as C1Y1 plus C2Y2. That's it. Okay, so we have to test it first. Solution, we say show that. So you have to find the second derivative substitute. So I'm going to go with the Y1 first, sine x, differentiated, Y1 prime. You have to do this on the test if it's going to be given. And the Y2 double prime would be negative sine x. Sorry, these are all Y1. So check it in this equation. Check into the Y double prime. So Y double prime plus Y equal to the 0. Check to see it's true. So that gives a negative sine x, and the y is sine x. So it is true. 0 equal to the 0. Okay, so you claim that the y1 equal to the sine x is a solution. Okay, any question? You have to do the same thing for the y2. Take the y2. Y2 is cosine x differentiated. That gives you negative sine. Differentiated again. That gives you negative cosine. Go to the equation, substitute. Y double prime plus y equal to the 0. Y double prime is negative cosine x. Okay, plus cosine x 0. 0 equal to the 0. So this means yes. Y2 equal to the cosine x is a solution. Okay, any question? Now they ask for the YC. General solution. YC. You know that. If you can prove that the run scan of this Y1 and Y2, if not equal to the 0, then the linear combination C1 Y1 plus C2 Y2 is the general solution. So the question is going to be, what is going to be the run scan of the Y1 and the Y2? Is it going to be a non-zero number or not? So check the run scan. You memorize the formula, write down in matrix form, it's up to you. You have to know it, okay? So this is it, the run scan of the Y1 and Y2 is Y1, Y2 prime minus Y1 prime Y2. It's very easy to remember. Now you already got all this information. Substitute, simplify. So it's equal to the Y1. Y1 was sin X. Okay, times it by Y2 prime. What's the Y2 prime?
Negative sign.
Negative sign. Minus Y1 prime. Y1 prime is, what Y1 prime? Cosine. Cosine X times Y2. It's a cosine X. Okay, so what's the result? Negative sine squared minus cosine squared. What do you have for this one? Simplify it, it's going to be negative 1. Negative 1 is not 0. That's it. So this means Y1 and Y2 are independent. Quickly, you know that. So Y equal to, okay, Y equal to the C1 Y1 plus C2 Y2, which is equal to the C1 sin X plus C2 cosine X. This is going to be the general solution of the equation, okay? The general solution of the, and you that. You see, from now on, this is your job. Always we need to prove independent. You have to prove it, it's a basis. Okay, so this is the way we're going to do it. So the next step is going to be how we're going to find Y1 and Y2. Okay, that's going to be the next one that we're going to do. Okay, next week. So as I told